Let's take a look at the principles of thin layer chromatography. The stationary phase in TLC is most commonly silica gel. The silica gel is sprayed onto a glass plate or plastic plate or aluminum foil. Let's take a look at the structure of silica. Do you think silica is polar or non-polar? When we look at the structure, we see silicon atoms bonded to oxygen atoms, and you can also see hydroxyl groups or OH groups on the surface of the silica. These OH groups can form hydrogen bonds or dipole-dipole bonds with other polar compounds, and therefore silica is polar. The mobile phase for TLC is usually a mixture of organic solvents, and we do not use water because water can actually dissolve the silica on the stationary phase. To help us select the solvents for TLC, we can take a look at the heliotropic series. This series lists the solvents in order of their power to carry the compound through the stationary phase. The solvents on top of this list are less polar. For example, you can see pentane, hexane, heptane. These are hydrocarbons which are non-polar. And as you move down the list, we see more polar organic solvents such as diethyl ether, dichloromethane, chloroform, acetone, and up to ethyl acetate and dimethyl sulfoxide or DMSO. The organic solvents in this range are usually used for normal phase chromatography range, and TLC is usually carried out in normal phase, whereas the solvents that are more polar at the bottom of this list are usually used in reverse phase chromatography, which I will explain later on. What happens in TLC? Let's do a short recap. The stationary phase in TLC is usually silica gel, which is a polar stationary phase. The mobile phase is made of organic solvents, and the organic solvents are relatively non-polar in comparison to silica. But as we have seen in the heliotropic series, there are a range of polarities for organic solvents, so the solvent can be chosen so that it provides a suitable polarity for the purpose. So in TLC, a few microliters of the sample solution will be spotted onto the TLC plate at the origin. The bottom part of the plate will be immersed in the mobile phase, and the liquid mobile phase will then move up the plate by capillary action. As the mobile phase moves up the plate, it also carries the analytes along with it. So for example, one analyte travels here, and another analyte travels a bit further. What makes one analyte travel a shorter distance and another analyte travel a longer distance? The distance moved is determined by the relative affinity of that compound for the stationary phase versus the mobile phase. So if a compound is more polar, then it would have a higher affinity for the polar silica gel, and so it will travel a shorter distance. So this compound over here is more polar, and that's why it travels a shorter distance. For a compound that is less polar, it would have a higher affinity for the mobile phase, which is less polar than the silica gel, and therefore it will travel a longer distance. So on the diagram, this green spot here is the less polar compound. The compounds on the TLC plate can be detected using fluorescence or UV light, as well as location reagents such as iodine vapor or ninhydrin spray. After the TLC is done, now let's look at how to interpret the results. The distance traveled by a compound can be expressed as the retention factor or RF. So let's take a look at this diagram which shows a compound that has traveled from the origin to the new position after the TLC has completed. The compound has traveled 2.1 cm. Let's compare this to the distance traveled by the solvent front. The solvent has traveled 2.8 centimeters. So the retention factor or RF would be the distance traveled by the compound, which is 2.1 cm, divided by the distance of the solvent front, which is 2.8 cm, and therefore the RF value for this compound is 0.75. Let's use this diagram to do some practice of calculating RF values. For compound C, the compound has traveled 1 cm compared to the solvent front of 5 cm, so the RF value would be 1 divided by 5, which is 0.2. For compound A, the distance traveled is 2 cm compared to the solvent front 5 cm, so the RF value would be 2 divided by 5 equals to 0.4. And for compound B, the RF value would be the 3 centimeters that it has traveled divided by 5 cm for the solvent front, and therefore the RF value would be 0.6. Also remember that because TLC uses a polar stationary phase, the polar compounds would travel a shorter distance, whereas the less polar compounds will travel a longer distance. So C is actually the most polar compound, and it has the smallest RF value. In comparison, B would be the least polar compound, and it has the biggest RF value. The RF values for a compound would be constant from one experiment to another only provided if the chromatographic conditions are also constant, such as the same solvent system, same adsorbent, and same thickness of the adsorbent, same amount of material spotted, as well as the same temperature. Sometimes it's difficult to keep all these conditions constant, so RF can also be reported as a relative RF instead, where RF is compared to another substance that is also run on the same plate at the same time. We can use TLC to separate a mixture of compounds, and as we have seen earlier, the compounds will form different spots on the TLC plates. So let's say we see two compounds on the TLC plate. The one with the larger RF is less polar, and the one with the smaller RF is more polar. This is because the stationary phase for TLC is usually polar, so the polar compounds would interact more with the stationary phase and therefore travel at a slower rate. TLC can also be used to quickly identify a compound. To do this, the sample is spotted on the same plate as the authentic compound. So let's say you have two spots, one spot for the sample and another spot for the known compound. Sometimes we may also want to do a co-spot, which means to spot both the sample and the known compound on that spot, just to see whether it forms one or two spots when the TLC is completed. So at the end of the TLC, if the compound in the sample is indeed the same as the known compound, you would see that they have the same RF, the spots have traveled the same distance. And if we did a co-spot, you would also see only one spot. As previously mentioned, for TLC, the stationary phase is most commonly silica gel. This is a very polar compound due to OH groups on the surface. As for the mobile phase is organic solvents, which are usually relatively non-polar. However, we can also see that there are a variety of organic solvents and they have different polarity. So the polarity of the solvents can be changed. The more polar the solvent, the further the polar compounds will be able to move up the silica gel TLC plate. Let's take a look at the diagram. The diagram shows three TLC plates which were developed using different solvents. In the first plate, the solvent used was a 7:3 ratio of hexane to hexyl acetate. Hexane is a hydrocarbon and it's non-polar. Hexyl acetate has an acetate group which makes it more polar, but since it is a 7:3 ratio of hexane to hexyl acetate, this solvent system is relatively non-polar. Now let's take a look at the next solvent system. It uses hexane to hexyl acetate as well, but the ratio is now 3 to 7. So it has more of the hexyl acetate, which is more polar. So comparatively, this is more polar than the first solvent system. For the third TLC, the solvent used is a 3 to 7 ratio of petroleum ether to hexyl acetate. Now, petroleum ether is more polar compared to hexane, so this solvent system is actually the most polar. Now, let's take a look at what happens to the TLC spots when the solvent system is changed. If you look at the first and second solvents, the more polar the solvent, then the further the polar compounds will be able to move up the silica gel TLC plate. We can see a big difference from the initial distance traveled in the first plate compared to the distance traveled in the second plate. Between the second and third solvent system, there isn't much difference between the distance traveled by the spots. So if the RF value of the compounds are already quite high, then increasing the polarity of the solvents is not likely to change the RF value by much. From this example, we can see that the solvent system can be changed so that different drugs can have different RF values, and we will tweak it so that we can get a good separation of the drugs or compounds to be analyzed. So between these three TLC plates and the three solvent systems, which is the best solvent system to achieve a good separation between the two compounds? The answer would be the first solvent system, because if you look at the first TLC plate, the distance between the two spots is actually quite different. The RF values are quite different, so you can achieve a good separation of the two compounds. Whereas if you look at the other two plates, the distance traveled is quite similar and the RF values are quite similar, so it does not achieve such a good separation between the two compounds. The stationary phase for TLC is usually silica, but this stationary phase can also be modified to give the system different properties. One modification is to treat silica gel with potassium hydroxide. Silica gel is polar, and compounds that are very polar will adhere very strongly to the silica. For example, amines, which could have the structure of, let's say, RNH2. This is an example of a primary amine. Amines can be ionized to form amine salts, so such as RNH3+. Ions are very polar and they would adhere very strongly to the silica. So we don't actually want the compounds to be in the ionized form. We would prefer the compounds to be in the unionized form. So treating the silica gel with potassium hydroxide would help to keep the amines in the unionized form because of the alkali environment. This prevents the formation of the amine salts which would interact too strongly with the silica gel. Another modification is to make the silica gel non-polar by treating it with silanes. When this is done, what happens is that the stationary phase now becomes non-polar and the mobile phase is relatively polar compared to the stationary phase. This is the opposite from traditional TLC, so this is called reverse phase chromatography. So in traditional TLC, the polar compounds will tend to travel slower and the non-polar compounds travel faster. But in reverse phase chromatography, it is the opposite. Polar compounds will travel further compared to non-polar compounds. After the compounds in a mixture are separated on a TLC plate, there are different ways to detect the compounds that are present on the TLC plate. One method of detection is using UV light or fluorescence. We can use TLC plates that have a material that can fluoresce when it's exposed to UV light. So for this type of TLC plates, we can view the TLC plate using UV light at 254 nanometers. If the compound on the TLC plate is able to absorb UV light, you will be able to see it on the plate as a dark spot. This method of detection is used in many pharmacopoeia tests because many drugs contain chromophores. Chromophores are part of the chemical structure of the drug that allows it to absorb UV light. Sometimes the compounds might naturally be fluorescent. In that case, you can view the TLC plate at 365 nanometers, and we will be able to see the compounds as fluorescent or bright spots on a dark TLC plate. There are also various chemical reagents that can be used to locate the compounds. One example is iodine. The TLC plate is put into an iodine chamber, which is a container that contains iodine crystals. The iodine crystals will form iodine vapor, which can then interact with the organic compounds to form brown spots. So, using these brown spots, we can visualize where the compounds are on the TLC plate. Iodine is used as a location reagent in pharmacopoeia tests for fixed oils and cetrimide. Another location reagent that we can use is potassium permanganate. Potassium permanganate, as you know, is an oxidizing agent, so it can be used to detect reducing agents. For example, reducing sugars or other types of reducing agents. One more location reagent is ninhydrin solution. When ninhydrin solution is sprayed onto the TLC plate, the primary amines will form pink spots and tertiary amines can be seen as yellow spots. Ninhydrin solution can also visualize some antibiotics such as aminoglycosides.